Next up, I want to invite Alex Ozdemir to the stage or screen. I never really know what to say. He's going to be talking about the taxonomy of circuit languages. We're going to learn more about ZK DSLs. Welcome,
Indeed.
Alex.
Yeah, thank you, Anna. And so, as Anna said, this talk is going to be a bit of a gear shift compared to the last three, in that we're not going to be talking about how you build zero-knowledge proof systems, but rather an important ingredient in how you use them, which is a language for expressing the property that you want to prove. So just a heads up, this talk is going to be a pretty dense one in its own way, in that we're going to talk about a lot of different languages, and I'm going to make a lot of statements about these languages. And I try to keep this talk up to date with the latest and greatest developments in circuit languages, but sometimes it gets out of date, and if you notice any inaccuracies, please let me know, and I'll fix the slides right after this talk. So let's dive into it. So taking a step back, the core problem that all of the ZK hack and zero-knowledge proofs are about in general is that you have some high-level idea that you want some property that secret data might have, and you want to prove that the data has that property in zero knowledge. So you want to go from this high-level idea to a proof. And the proof systems that we've been discussing so far today, they will help you write that proof, but the problem is that they probably don't consume the high-level idea as it exists in your mind. No, instead, in order to use a zero-knowledge proof system, you have to write down a circuit for the property that you want to prove. And so that creates this problem. How do we go from high-level ideas to circuits? And this is where circuit languages come in, and this is what this particular talk is going to be about. Circuit languages are a really busy area right now. Over the course of the past 8 years, there's been a real Cambrian explosion and exponential growth in the number and the richness of circuit languages. Here I just have, I'll put up a timeline that shows some prominent languages and when work on them began. Going back to the early 2010s, we've got tools like GadgetLib, which were really sort of like macro assemblers for assembling different gadgets within a circuit, and Pekin, which compiled from a fragment of C to a particular kind of circuit. And then just in the course of the past year and a half, 2 years, there have been a whole host of languages that have been developed. Noir, Cairo, Leo, Zinc. And so clearly there's a lot of stuff going on in this space. And what I try to do in this talk is compare and contrast these languages with one another, look at ways in which they're similar and different in order to better understand the space as a whole. So the first question that one might ask about any circuit language is what kind of circuit that language is intended to produce. And all of the languages that I'm going to be talking about in this talk target some kind of arithmetic circuit. That is a circuit where the values in the circuit, the wires, carry finite field elements, and the gates do some kind of algebraic operation, like multiplication or addition. So some circuit languages target essentially just simple arithmetic circuits. There's a constraint format for this called rank 1 constraint systems, or R1CS. In this case, you can have a circuit with additions and multiplications, and the additions are essentially free, and the multiplications have unit cost. But there's another kind of arithmetic circuit format called Plonk, which is I call it Plonk, but it's the kind of circuits that the Plonk proof system can handle, where multiplication and addition both have unit cost. So in some sense, it seems a little bit worse than R1CS. But there's also some substantial advantages. Namely, the proof system can support custom gates that do more complicated operations. And also you can get randomness from the verifier, which you might be able to use to check some property or do some computation more efficiently. So these two formats, R1CS and Plonk, these are true circuit formats in that they describe some bounded computation. But there's another format, AIR, or arithmetic intermediate representation, that's used by Stark-based proof systems or similar. And the idea here is that you've got some arithmetic circuit. You're not just going to compute it once. You're actually going to apply the circuit repeatedly. So the circuit produces the same number of inputs and outputs, and you're going to repeat the circuit time after time. And so when you're designing for a repeated circuit, you might imagine that you want to generate the circuit somewhat differently. You want to try to take advantage of those repetitions. So I call these kinds of circuits RAM-like circuits, because since the intent is to repeat them, you want to design them a bit differently. And the languages differ in that different languages target different kinds of circuits. There are a variety. Most of the classical languages target R1CS, Spellman, Snarky, GadgetLib, etc. There are also some more recent languages that target the Planck circuit representation, so Noir and UPA, the older Planck arithmetization, and a library for building it. And then there's a separate branch of the tree, languages that are trying to target air. And so there are some lower level ones like AirScript or AirAssembly, and some slightly higher level languages like Cairo. So that's one axis, which is the kind of circuit that you're producing. Another axis on which the languages differ is what the languages are like at a high level. And so for discussing what the languages are like, I think it's useful to separate languages into three different types. There are essentially libraries where the language isn't a standalone language. Instead, you have a library inside some other language. So you might have a Rust library for helping you build circuits, or a C++ library for helping you build circuits, or an OCaml library for helping you build circuits. So that's sort of actually where this project really started. Originally, when people were trying to build circuits, they didn't want to go through the work of building a standalone language. They just figured they would create a library in their favorite programming language. But beyond libraries, people have designed what I would call hardware description languages, or HDLs, which are essentially languages for building circuits that are in the style of Verilog, which is a language for building digital circuits. The idea is to explicitly describe the layout of the circuit and what is connected to what. This is in contrast with what I would call a programming language, where there's some notion of variables and functions and mutation. So something that's trying to emulate Rust. And the different languages differ in that they fall into different buckets here. So the languages that are really more of libraries are Bellman, which lives inside Rust, GadgetLib, which lives in C++, Snarky, and UPA. And the dominant hardware description language for zero-knowledge proof systems and their associated circuits is CIRCOM. And then there are a whole variety of more recent languages, I would say, are all trying to be true programming languages. And one thing I want to emphasize is about this separation is that it's somewhat blurry. The boundary between a library and a programming language can be a little bit ill-defined. Libraries sometimes start to impose their own semantics, acquire their own syntax, and look somewhat different from their underlying language. And I think Snarky would be a good example of this. Snarky is technically OCaml, but it looks rather different. Nonetheless, this distinction can be useful. So when we talk about the move towards programming languages, a natural question is what kinds of programming language features are hard to support when you're compiling the circuits, and therefore are omitted from some languages that target circuits. One feature that's hard to support in a circuit is the notion of a mutable variable. In particular, inside a circuit, there are no mutable variables. Every value, every wire gets computed exactly once. And so this can be a challenging thing to represent in a circuit, and not all languages support it. So in particular, the libraries and the HDLs, they do not support mutable variables, and most of the programming language circuit languages, they do support mutable variables in some form. Another important feature of any programming language is the set of types that language has native support for. So if we look at Rust, which is this code is a snippet from Rust, then we have things like Booleans, we have machine integers, integers of fixed width, and then we also have floating point numbers. And not all of these are supported by circuits, by various circuit languages. So almost every language supports finite field elements because ultimately we're compiling to circuits over a finite field. Some tools like Bellman, GadgetLib, UPA also add on Booleans, and then some languages go even beyond that and add support for machine integers. So fixed width integers that can overflow and behave exactly like int or short or char in C. Another feature that can be challenging, even more challenging to support, is the notion of an if statement. So in a language that's going to run on your CPU, an if statement is really easy to support. You just have to emit conditional jumps in the assembly that you're producing. But when you're compiling to a circuit, if statements can be hard to support, because if you have some kind of side effectful operation, like a mutation inside the if statement, sometimes that mutation happens and sometimes it doesn't. And this distinction is made on a data-dependent basis. In this small program, we are either squaring base or not squaring it, depending on whether the X bit is set. This is actually quite challenging to support inside a circuit language because you can't just view the mutated variable as like a new version, like a new variable entirely unrelated to the previous one. Instead, you have to do some kind of state merging where you sort of compute the change and you keep the original version and then you combine them. And so it's actually somewhat rare for circuit languages to support if statements that have side effects inside of them. And so the languages Leo and Pekin and Cairo, all of these support it. And there are a variety of other languages that support ternary operators, so if then else's, but true if statements. Those are actually somewhat rare. Another feature that you might want from a language is the ability to define your own structures. When we implement applications, we come up with objects that are important to the application, but aren't important enough to go into the language itself, or aren't as universally agreed upon to go into the language itself. And so it's important for languages to have some ability for users to define their own kinds of structures. On this slide, I have an example in Rust that represents a compressed elliptic curve point. So it's an elliptic curve point where we're storing the x-coordinate, but we're not storing the whole y-coordinate, we're just storing whether it's positive or negative. And the idea is that this might be a more succinct representation of the elliptic curve point. You might come up with other kinds of structures that are important to your application, perhaps a transaction, a vote, something like that. Not all languages allow you to define these kinds of structures. So Noir and Circom, to my knowledge, do not. Some languages actually get user-defined structures for free. These are circuit languages that are really libraries in some kind of host language. And since the host language has some notion of a user-defined structure, the circuit language, the circuit DSL, gets it as well. So Bellman, GadgetLib, Snarky, UPA, all of these fall into that bucket. And then for the standalone circuit languages, some of them do support user-defined structures. So Pekin, Socrates, Zinc, Cairo, Leo, all of these support some kind of user-defined structure. Another feature that can be challenging for circuit languages to support is the notion of an array. So when you're compiling to a CPU, an array is just a contiguous region of memory that you can access via pointers. But in a circuit, it's a little bit less clear what an array should be. And in particular, the most challenging thing to handle when you're interacting with an array is the notion of variable indexed accesses. So when you're taking the array and you're either reading from it or writing to it at a data-dependent location. So in this snippet of code, we've got an array of length 4, and we've got an index I. And we access that array at that variable index, and then we write back to it at that same variable index. This is pretty challenging to support when you're compiling to circuits, because in a circuit, you don't have a built-in type for an array, and you don't have any notion of memory. So it's like, well, what are you going to do? Nonetheless, some languages do try to support it one way or another. So there are a variety of languages that support arrays with constant indices, but when it comes to variable indices, Socrates supports variable indices by doing a linear scan over the array. So every time that you try to access an array at some index, it just checks every single spot and says, is this the right spot? Is this the right spot? Is this the right spot? And so on. And then it turns out there are some better strategies based on routing networks or other kinds of permutation checking machinery. And Pekin and Cairo support arrays via these more advanced techniques that yield better performance. Okay, so this has been a really a whirlwind talk, a lot of information very quickly. I think it's worth taking a step back and at least from my perspective, advocate an approach to building circuit languages that I think is useful. Okay, so what can we, when we think about circuit languages, what lessons should we take away? The first lesson that I think that we should take away from the richness of this ecosystem is that we need to keep exploring. There are a lot of different languages. They're somewhat divergent in terms of the design decisions that they've made, and it's not clear yet what the right approach is. People will continue to build new languages. They continue to have good ideas. It seems clear that we need to continue to explore the design space of circuit languages. The second thing that I want to take away is that when you're compiling to circuits from a high-level language, this is actually a pretty challenging task. There are certain features, like array indexing, that are very challenging to support, but that programmers really expect and that programmers know how to reason about. So up here on the slide, I have a visualization of the kind of routing network that is often used to check array indices. This is just one example, but many of the features that I described during this talk are quite challenging for circuit languages to support. I think that in the same way that we're trying to explore the design space for what the language should look like, what the syntax should be, what the semantics should be, we're still trying to explore the design space for compilation as well. We continue to come up with new compilation techniques for better representing different constructs inside a circuit. And then this work is challenging. So given that there's still a lot of need for exploration and that the work itself is very challenging, I think that one interesting idea is trying to share infrastructure between different circuit languages. So we might ask, is there some kind of common library or common infrastructure that we can build that would help us as we build compilers that map various high-level languages that either exist or that we come up with to different kinds of circuit representations? And I think that it is possible to build infrastructure that fulfills this promise in some sense. I've been working on this with some friends. We call the project Circe for Circuit Compiler. There's a link to a paper as well as a link to the GitHub repository on the slide. And what we should hold in our mind as the North Star when we do this kind of unifying compilation work is a project like LLVM, which is trying to make it easy to compile from various high-level languages to different kinds of assemblies. What we want is something like LLVM, but something that allows us to compile from different kinds of circuit languages to different circuit representations instead of assemblies. Okay, so this is the end of the talk, and I'm happy to take any questions that people have. Okay, is there a logic behind which features of these circuit languages support? Which features these circuit languages support, or is it simply due to implementation difficulty? I think that there's sort of two factors. So yeah, so one of the factors is just implementation difficulty. Some of the more advanced features are somewhat challenging for compilers to support, and so people just don't do it. I think that's most of the time the answer. In some cases, people will make claims like omitting variable mutation makes it easier for the programmer to understand. And there might be some truth in that, but I would generally say that we should allow programmers to do more things, not less things, because I think that sort of the greatest barrier to new programmers using circuit languages is those languages being very different from things like Rust or C that programmers are already used to. So I think that the best thing to do in the long term is to support as much as we can. Yeah, so this is a question. Is accumulation schemes here, a term I've only heard recently, related to persisting a value on each recursion? Yeah, so, okay. So when you say accumulation schemes, I think that what you're talking about is the tool for building recursive arguments or, in general, proof-carrying data. But closely related are accumulators, or cryptographic accumulators, which can be used to implement array-like or memory-like abstractions within a circuit. So accumulation schemes, not particularly relevant to the design of circuits, to my knowledge, but accumulator schemes, highly relevant. And this is a kind of cryptographic machinery that you can use to prove that you're interacting with some memory in a fashion that's consistent, in that, like, if you write something and then later read it, you get the same value. Oh, my audio seems to be broken. I'm glad that you guys can hear me. I cannot hear you.
No, I'm muted. Sorry, my bad.
Okay.
It does seem like there's some last questions that just rolled in. I don't know if you got a chance to answer these ones. One is about Cairo. Yeah, here, actually. This is not about Cairo. Another one's about
okay. Someone must have written or already worked on some kind of LLVM-based system. So there is a little bit of work in this direction. Actually, not for zero knowledge, but for MPC. The project is called CBMC MPC, and so what they try to do is build an MPC compiler based on CBMC, the C-bounded model checker, which is sort of based on LLVM. And the challenge that you run into here is that LLVM, because it targets assemblies, is sort of doing all the wrong things. So in particular, assembly languages have extremely efficient memory and extremely efficient jumps. And so LLVM tries to use those things better, and all those things suck in circuits. So LLVM sort of takes you the wrong direction. In terms of sort of building a new compiler infrastructure that's oriented around the design of circuits and not assemblies, I guess we've worked on that, but I'm not aware of a lot of other work that's trying to do the same thing. There are some sort of vaguely related things very far from cryptography in the realm of model checking. And then understanding Cairo's place in all of this. Yeah, so Cairo is a little bit different, right? Because it's targeting error. It's targeting these computational models that are intended to run continuously. And that's why, yeah, I have sort of the Cairo and some other languages that target AIR as being somewhat separate from the rest of the circuit languages. But I think it's worth noting that even in the case of Cairo, the arithmetic intermediate representation, AIR, that does describe some circuit that's going to be repeatedly applied. And so some of the same techniques might be useful when compiling Cairo to AIR or similar languages to AIR.
All right. I think that wraps up the questions. Unless there's, yeah, I think we're good. Alex, thank you so much for this talk and for sharing. Yeah, I'm seeing some clapping in the backstage from sort of cool looking aliens. Anyway, yeah, thanks a lot. And